In this section of the unit, we're going to discuss the chemistry of soil. Many complex chemical reactions occur in soil. The metabolism of microorganisms, plants, and small animals living in the soil contribute to these chemical reactions, as well as the interactions of soil with the atmosphere and groundwater. Soil chemistry determines the ability of soil to provide nutrients to plants. As discussed in the previous topic, soil particles bind to nutrients and release them to plants. Plants are producers, so consumers, including all animals, depend on the plants, which depend on the soil chemistry. Colloids. The surfaces of particles in the soil determine the soil's chemical properties. Because clay is the smallest mineral in soil, these particles bind ions more efficiently. Therefore, fertile soil must contain clay particles. Clay particles are insoluble. Clay particles and the mixture that they are a part of are referred to as colloids. Pictured is a colloid with a positively charged surface, which you can see here. This is like a clay particle with a positively charged surface, attracting anions or negative particles. Ion exchange capacity. The colloids in soil allow it to have an ion exchange capacity, which is the ability of soil to attract and release ions. Although the soil particles attract ions, they easily surrender the ion to other charged particles in the soil water. This is important because it allows these nutrients to be absorbed into plant roots. There are two types of ion exchange capacity: cation exchange capacity, or CEC, and anion exchange capacity, or AEC. Cation exchange capacity, CEC, is the measure of how many cations soil can retain and release. Cations are positively charged ions, so they are attracted to the soil clay particles that have a negative charge. Key cations in the soil include potassium, K+, which is needed to activate enzymes that are involved in plant growth and photosynthesis. Calcium, or Ca2+, is needed to build the cell walls of plant cells. Magnesium, Mg2+, is needed for chlorophyll molecules to perform photosynthesis. And sodium, Na+, is generally not needed by plants, but some plants use it to promote metabolism and concentrate carbon dioxide. Clay particles can have negative charges because the elements they contain may be replaced by less positive elements. For example, phyllosilicate minerals in some clays have aluminum. If the aluminum is replaced by magnesium, there will be a net negative charge on this clay molecule because the charge on the magnesium is less than the aluminum. Another way that clay particles can become negatively charged is if a hydrogen ion, H+, are removed from the particle, leaving behind a negative charge. Pictured below are negatively charged soil particles. You can see all these negative charges along the outside of the soil particle, attracting positively charged ions. So you can see this positive calcium ion attracted. There are some potassium ions, magnesium ions, all attracted here. And then here you can see the exchange. So this is the exchange that's able to happen. This calcium exchanged for this magnesium. Okay, and now this magnesium is in the water, in the solution. Cation exchange capacity and soil pH. Soil pH is the measurement of how acidic or basic the pH of the soil water is. If the soil pH is high or more basic, then cations exchange capacity will increase because more hydrogen ions will be pulled off the soil particles into the surrounding solutions. If the soil pH is low or more acidic, then the cation exchange capacity will decrease because hydrogen ions will bind to the soil particles, making them less negative. Soil pH is best between 6 and 7. This will allow cation exchange capacity to be at an adequate level. If the pH is too high, then certain nutrients cannot dissolve as easily in the soil water mixture. How plants collect cations from the soil. An advantage with soil that has a high cation exchange capacity is that the cations will not wash away easily. When plants need cation nutrients, their roots will release hydrogen ions into the soil, making it more acidic and lowering the cation exchange capacity of the soil. The more acidic soil water solution will push cations away from the soil particles and into the solution. Once in the solution, the floating cations can then be absorbed into the plant roots. Anion exchange capacity, or AEC, is the ability of soil particles to hold and release anions. Anions are negatively charged ions, so they are attracted to soil particles that have a positive charge. Anions include nitrates and phosphates. Nitrates contain nitrogen that is needed for plants to build amino acids, which are used to build proteins, which are required to build tissues. Phosphates contain phosphorus, which is required to build nucleic acids. Anion exchange capacity in soils is generally less than cation exchange capacities. This is okay because anions that plants need easily dissolve in water and are readily available for plants. Anion exchange capacity is higher for soils that contain iron hydroxide and aluminum hydroxide. These compounds are able to exchange their hydroxide ions for other anions that are less negative. This results in positively charged soil particles that are able to attract anions. Anion exchange capacity depends heavily on soil pH. When the soil pH decreases or becomes more acidic, anion exchange capacity increases. Hydrogen ions from the acidic soil water solution attaches to the soil particles, making them positively charged. Tropical rainforests are acidic. The soils of tropical rainforests are acidic due to the high rainfall that washes out nutrients. The rain is usually acidic and therefore decreases the soil pH. The soil particles become positively charged and their anion exchange capacity increases, but the cation capacity decreases. How do rainforests then stay healthy if the soil is nutrient poor? In the rainforest, the tree roots do not grow deep into the soil. They rely on the nutrients of recently decomposed leaves and other organisms close to the surface. Because soil is nutrient poor in the tropics, farmers have developed ways to make the soil healthier for growing crops. In order to increase the pH of the soil or decrease the acidity, farmers will add lime, a combination of calcium and oxides, usually calcium oxide or calcium hydroxide. The amount of lime needed to neutralize the acidic soil depends on the amount of free acid in the soil water solution, as well as the amount of acid that will be formed when the cations are pushed off of the soil particles. To make soil hold and retain nutrients, farmers add biochar to the soil. This has been done since ancient times. Buffering capacity in soil. Soil that is acidic is nutrient poor and has low cation exchange capacity. Soil becomes acidic due to high rainfall, decay of organic matter, and harvesting of crops that absorb cations. The buffering capacity of soil is the ability of soil to resist changes in pH when acids or bases are added to it. Increasing the buffering capacity of soil reduces the chance of soil becoming acidic. Soil that is rich in clay minerals has a high buffering capacity because it binds ions that would otherwise change the soil's pH. Adding lime to soils that are poor in clay minerals can increase their buffering capacity. Soil salinity is the amount of dissolved salts in the soil water solution. Soil salinity tends to be higher in low-lying areas, arid regions, or in areas that are irrigated. Plants that grow in soil with high salinity tend to have stunted growth and withered leaves because they have to work harder to absorb the nutrients they need. Managing soil salinity is difficult. One method is leaching, washing the salt down below the root system, but this requires a lot of low salt water. Applying mulch to an area can help reduce the evaporation of fresh water and stop salinity from increasing.